let's continue to discuss the flux of the current density of the surface. Now consider a conducting region V bounded by closed surface A as shown here. An outward flux of charges crossing the closed surface per unit time must be equal to the rate at which the charge is decreasing in the bounded region V as expressed by this equation. We call the equation of continuity. From this equation, we understand that the total charges flow out of the surface A in a unit time should be the surface integral of J over the entire closed surface and also equal to the rate at which the charge is decreasing inside the surface. So we have a minus here. Based on the equation of continuity, if the net change of the charges inside the closed surface is zero, then we have a steady current, which means the net flux of the current density over the closed surface is zero. That means the number of the current density lines entering the surface is equivalent to the number of the current density lines leaving the surface. Now, if the ends of a conducting wire are connected to form a loop, all points on the loop are at the same electric potential. Hence, the electric field in the wire is zero. Because the electric field is zero, there is no net motion of charges through the wire. Therefore, there is no current. If the ends of the conducting wire are connected to the two plates carrying the charge with equal magnitude and opposite sign, potential difference between the ends of the loop is built up, creating an electric field within the wire. The free electrons in the wire is then moving under the action of the electric force, and thus a current is produced. However, in this case, the potential difference will be decreasing to zero when more and more electrons move onto the positively charged plate to cancel the positive charges on the plate. Hence, when the electrostatic force only exists in the circuit, we cannot maintain a steady current. If we connect the ends of the wire to a battery, the potential difference maintains a steady value. The steady current is then obtained. So, we must have non-electrostatic force to have a steady current. The battery is a power source that produces non-electrostatic force. Non-electrostatic force could move the positive charges from the negative terminal to the positive terminal to maintain the potential difference in the wire. Here, EK is defined as the non-electrostatic force on the unit positive charge. And also, we introduce a new quantity, electromotive force, EMF, which is defined as the work done by the non-electrostatic force on the unit positive charge along the closed loop L. Outside the power source, only electrostatic force exists. This term is equal to zero. Therefore, the value of EMF is equal to the work done by the non-electrostatic force on the unit positive charge from the negative pole to the positive pole of the power source. After studying the electric current, we could return to magnetism. We are going to discuss the magnetic field next lecture.